Hello, I am Berkant Karasoy. I am physics major. Uh, in this experiment, I examined the displacements, velocities, and acceleration of masses in double Atwood machine with spatial mass distributions. While I'm calculating displacements, velocities, and accelerations, I used mainly Newton's second law and a little bit of Lagrangian method to derive some equations. Um, in my experiments, I observed the mass distribution with three cases. Also, in these experiments, mass of the pulley are didn't neglected, but the air friction, and the rotational motion of the pulley are neglected. So let's begin with the first case. The right side and the left side of the system have equal masses. As expected, the system doesn't move. No matter how I try to move it, the system remains stationary because of the forces are balanced. Consequently, displacement, acceleration, and velocity are all zero. In case 2, all masses are equal, but the system isn't balanced. As expected, it moves to the left. By measuring displacement and time, we can calculate the acceleration of each mass. In the last case, all masses are different, and the net force is on the left side. By measuring the initial motion, as in case 2, we can calculate the acceleration of each mass. This table shows the masses used in the experiment. And this table shows the displacement of each mass in each case. And this graph provides information to us the velocities of the masses in each case. This is the first graph, velocity versus time for all masses in case 1. This is the second graph, is also a velocity versus time graph, with each colored line representing a different mass in case 2. The final graph is a velocity versus time graph for case 3, where each colored line represents a different mass. This table shows the experimental accelerations for each mass. Accelerations are determined by calculating the slope of the velocity versus time graphs for each mass in each case. The next table represents theoretical values of accelerations calculated using formulas derived by Newton's second law and the Lagrangian method. And finally, the last table provides information about the percent error in acceleration. Most of the accelerations have an error rate of less than 10%, but mass 3 has an error greater than 25%. This discrepancy may be due to the sensitivity of the measurement devices. Finally, the results have general agreement between the theory and experiments. Thanks to these experiments, we can observe the motion in double Atwood machines successfully.